Okay, Jenny, let's start. Before you um, start doing Laplace inverse, what you have to remember is how to do partial fractions. Now, why you need partial fractions? The reason behind needing partial fractions is because in the formulas table of the Laplace inverse, you won't find a formula that actually has this shape, or actually has this shape, or this one, or even this one. What you have is separated fractions. And when I say separated fractions, I mean the Laplace inverse of the sine, the cosine, and the exponential. So you won't find this. So what you need is to strip this fraction into partial fractions. Okay, now, to do so, we have to remember some rules. Okay, now, first thing to notice here is when you have these partial fractions, you have to first recognize the denominator. Actually, the partial fractions is more related to the denominator. The numerator, it doesn't matter for the moment. But the denominator is actually telling you what kind of partial fraction you will have. For example, here is s minus 2 and s plus 2 as a multiplication. So here, this is a polynomial of second degree, and you will have the roots like this: s equal to 2 and s equal to minus 2, s1 and s2. So because it is second degree, you will have two roots, and then here comes the partial fractions. You will have two partial fractions. How are those partial fractions? They are like this: a over s minus 2 plus b over s plus 2. Those are the partial fractions. Okay? Now, the question is, what will be the values of a and b such that when you do the common denominator, the values of a and b such that they are 7s plus 4. What is the combination of a and b so that you will get 7s plus 4? Okay, for the moment, that is not important. What I want to make clear here is how to build the partial fraction. So this is for the first root, and this one is for the second root. All right. Okay, so that's very important, and this is real partial fractions. Okay, now another example. What happens if you have something like this: 7s plus 4 divided by s minus 2, s plus 2, and let's add another, s minus 3, for example. So you will have s1 is equal to 2, the first root, s2, the second root is minus 2, just like the previous, but you will have a third root, which is 3. All right. Because they are real partial fractions, real roots, the partial fractions will be something like this: a over s minus 2 plus b over s plus 2 plus c over s minus 3. And that is the partial fractions, a, b, and c. Again, the question is, what will be the values of a, b, and c such that when you do the common denominator, you will get this fraction. Okay, now, here comes the reason why you need these in partial fractions, because you won't have a formula of the Laplace inverse like this. Okay? You won't find a formula like this. What you have is formulas for this, this, and this. And those three is actually exponentials. Alright? But we need to find the values of a, b, and c. But that is not important for the moment. Okay, this is two examples of real partial fractions. Now let's see what happens when you have real but repeated roots. Okay, now here's this example. Here, s minus 2, the root is actually s1 is equal to 2, but the s2 is equal to 2 because it is twice here. You have repeated case. Okay, the third root will be s3 is equal to minus 2. That is this root. Okay, now the partial fractions will be something like this. It's going to be a over s minus 2 to the power of 1 plus b over s minus 2 squared plus c over s plus 2. Okay, now the last one is the partial fraction for this root. But what about this one? Well, this one, s minus 2, is for the first root, and this one is for the second root, which is repeated. Now, we cannot make like this, s plus 2 power 1, because these two partial fractions will be the same. And because you have the same partial fraction, then there is no need to write a and b, it's just one single partial fraction. But that is not sufficient because you need second degree. So that is why you write here second power here. So you have to complete the polynomial, the first power 1 and the other one power 2 for the second root. And this is the partial fractions for this repeated root. This is the rule. And again, the denominator is third degree, power 3. You have 3 roots, 2 of them are repeated, and you will have 3 partial fractions. So that is the rule. The number of roots is equal to the number of partial fractions, and it's going to be the number of constants here. What are the values of those constants? Okay, we will see that in the next video. For the moment, I want to clarify what is the partial how to build the partial fractions. Okay, now for this example, you have s minus 1 to the power of 3, so it is repeated 3 times, and then you have s plus 2 squared, so the root is s equal to minus 2 but 2 times. So here s1 is equal to s2 is equal to s3, and that is equal to 1, and then s4 and s5 is equal to minus 2. Alright, so you will have the power of the denominator is 5, and you have 5 roots. 1 is 3 times repeated, and the minus 2 is 2 times repeated. So now you will have to have 5 partial fractions, and it's going to be something like this. It's going to be a over s minus 1 to the power of 1, so that is the first root, and then plus b over s minus 1 s squared, that is for the second root, and then c over s minus 1 to the power of 3, and that is for the third root. And then here 1, 2, and 3 comprises all these in one together. And then I'm going to continue over here, plus, this is 2 times, so it's going to be a, b, c, d over s plus 2 power 1, plus a, b, c, d, e over s plus 2 squared, and then you have covered the 2 roots here. And again, engineers, we cannot make this 1, and we cannot make this 1. The reason is because these 3 is the same fraction, so there is no distinction between them. The way to this guys is 2 and number 3 here. This is different from this, and this is different from this, and it still has the same root. Alright, s equals to 1. So those are for the repeated real roots. Okay, what about when you have imaginary roots, which is this case, s minus 1 over s squared plus 1. Here, this one, the s1 and 2 is equal to plus minus I, and s3 and 4, because it is 4 degree, so you will have 4 roots, is going to be plus minus 2i. But here the roots are imaginary. Okay, now how are we going to build the partial fraction for this? Okay, the rule for this kind of fraction is going to be something like this: as plus b over s squared plus 1, and this covers this one, the plus and minus I, and then plus cs plus d over s squared plus 4, and this covers the other 2 roots. Now you are supposed to have, because this is 4 degree, you are supposed to have 4 partial fractions, and you do have it. Here is 2, and here is 2 partial fractions. One contains the s and the other is without the s, and so on. But this one is for I, and this is for 2i in the imaginary roots. Okay, so that's the rule for partial fractions in the imaginary roots. What if you happen to have a combined case? Okay, a combined case, let me place like this: s over s squared plus 1, and then s squared, and then s minus 1. Here what you have is an imaginary root, but it's repeated twice, and then you have a real root. Okay, so s1 and 2 is equal to plus minus I. This is for the first one, but then s2 and 3 is going to be plus minus I, because it is repeated, you have the square here, and then s5 is equal to 1. So because the power of the denominator is 5, So you have five roots, and then you will have 5 partial fractions. How are you going to have 5 partial fractions like this? As plus b over s squared plus 1 power 1. Now we are going to write this the other two. cs plus d over s squared plus 1 power 2, and that comprises the second the other two repeated roots. And then the fifth real root is going to be abcde over s minus 1. And then when you do the Laplace inverse, you are going to apply the Laplace inverse to this, and this, instead of applying the Laplace inverse of this, because you cannot solve this in the Laplace inverse because you don't have a formula with this shape. You will have a formula for this, and this. Alright? Now, this is the kind of partial fraction that you are going to see. Real repeated roots, and imaginary roots. Now, on the next video, we will see how to calculate the values of A, B, C, and D for each one of the cases. All right, we will start with the real partial fractions, how to find the A, B, and C on the next video.